So we now have Antonio Gomes for BitDrone from Queen's University.
Hi, everybody. Before we start, sorry for the images being cut a little. Apparently, we're having projector issues, but I'm here to present BitDrones, a platform that uses 3D nanocopter displays as interactive self-levitating programmable matter. I'm Antonio Gomes. I'm a PhD candidate at the Human Media Lab, Queen's University, and my co-authors are Calvin Rubens, Sean Braley, and my supervisor, Roel Vertegaal. So in this paper, we will discuss 3 types of BitDrones that facilitate human-drone interaction. In the paper, we describe a number of unimanual and bimanual input techniques. We demonstrate user interface elements, such as self-levitating cone trees and tangible building blocks. And we allude to a number of potential application scenarios and depict future directions towards creating high-resolution, self-levitating programmable matter. So the thought that computer interfaces might someday physically embody user interactions has been around for a very long time. In 1965, Ivan Sutherland envisioned the ultimate display, a room within which a computer can control the existence of matter. For example, a chair in such a room would be good enough to sit in. Handcuffs displayed in such a room would be confining, and a bullet displayed in such a room would be fatal. In the following years, programmable matter would come to be described as a collection of small cellular automata nodes capable of geometrically shaping themselves in 3D space to create any kind of material structure. Since then, there has been research towards this goal under various monikers, such as Claytronics, a concept that envisions nanometer-scale computers called Claytronic atoms, which can interact with each other to form interactive, tangible 3D objects. Organic user interfaces, whose goal is to move beyond flat interfaces and to contextualize interaction in an object's physical shape. And radical atoms, a vision that alludes to human interaction with future dynamic materials that are computationally reconfigurable. However, much of the progress towards building these Claytronic atoms has been theoretical in nature. How to create a massively parallel system of atoms capable of displaying two-way immersive physical experiences is still an enduring research goal. So before we delve into this whole field of human-drone interaction, there's a number of papers that we cannot do justice to, so I would like first to briefly introduce research in areas that inspire the design of BitDrones. So tangible user interfaces were first introduced as an effort to augment the real world by coupling digital information to everyday physical objects and environments. However, tangible user interfaces have limited ability to display changes applied to the physical objects by software processes or remote users. By contrast, augmented reality systems use partially transparent displays to superimpose graphics onto real objects or environments. HoloLens, for example, maps the space around the user, allowing the system to simultaneously model its environment, as well as sense markerless gestural input. Mixed reality is a special class of augmented and virtual reality interfaces, wherein real and virtual world objects are presented together in a single display. With BitDrones, we propose working towards merging the local, remote, physical, and synthetic in such a way that they become one and the same. Actuated shape displays provide novel opportunities for experiencing and interacting with digital content in the physical world. While they can provide a bidirectional interface between bits and matter, they are limited in the kind of shapes they can render, such as overhangs or shapes with holes inside their structures. In recent years, there's been significant effort towards developing a new generation of computer interfaces capable of programmable self-assembly of complex shapes. However, they are limited to rendering shapes in 2 dimensions. And furthermore, they're fairly slow. This is sped up to 20 times, if I recall, and it takes a total of 10 hours to form this shape. So we can't really have real-time visualizations of 3D data. And to address this limitation, researchers proposed the use of magnetic and ultrasonic self-levitation. However, while these techniques can be effective to move a number of catons simultaneously, they pose distinct limitations to independent motion of multiple catons. More recently, as drones become commonplace, researchers have been investigating what are the most effective methods to facilitate human-drone interaction. While there is a body of work that explores interactive swarms of drones, augmented sports, and flying displays, they lack support for multimodal communication between the drone and the user. Our goal is to create interactive, self-levitating, tangible user interfaces with multiple building blocks capable of physically representing 3D data on the fly. So to inform the design criteria of the development of BitDrones, we consider the following design criteria. We designed BitDrones in a modular fashion, allowing users to build structures of varying granularity, depending on the complexity of the object. We compensate for the lack of density, given the small numbers of BitDrones we can fly at any given time, by allowing the use of higher resolution sub-voxel imaging drone-mounted displays. While BitDrones have the ability to follow gestures, as well as track users inside the tracked space, an important design criteria was for each drone to respond to direct touch. This allows users to directly interact with our system without prior knowledge of predefined gestural interactions. Due to their sparseness, we designed BitDrones in a multitude of form factors, allowing users to efficiently build structures of different density and complexity. BitDrones can be embedded in a 3D printed structure, including but not limited to cylindrical, rhombic octahedral, and spherical. So in BitDrones, each nano-quadcopter represents a caton that can autonomously roam anywhere within a 4 cubic meter Vicon space. Each BitDrone is powered by an Atmega 328P microcontroller with built-in accelerometer and gyroscope for self-stabilization. XP Wi-Fi radios support bidirectional communication between each drone and the host computer running the BitDrone's operating system. Each individual drone is also augmented with a unique set of infrared markers that allows our motion tracking system to capture each drone's position with sub-millimeter accuracy. And finally, our PID control loops are individually tuned for each type of drone, and they handle the drone's behavior as it flies to a target destination. So we developed three different types of BitDrones that we use in different contexts, each capable of representing or displaying information at different resolutions. PixelDrones, which are our smallest drones, carry an RGB LED, which provides a colored voxel to the user, and can optionally be equipped with an OLED display that allows them to show text labels and simple graphics. ShapeDrones carry a lightweight mesh structure spun around a 3D printed frame that acts as the diffuser for an RGB LED. Larger, allowing the entire shape to be lit up in color, that act as a larger pre-shaped voxel. ShapeDrones allow the use for the use of larger, more complex shapes that would normally be difficult to produce using a sparse set of drones. And DisplayDrones carry a lightweight 720p flexible OLED touchscreen, which allows for a high-resolution flying graphical user interface. A small camera mounted on the front of the DisplayDrone allows it to capture real-time video, providing support for real-time telepresence applications. Each BitDrone has its own set of PID control loops, which it uses to control its position in 3 space. Every PID gain settings are tuned to the type of copter being flown. In addition to tracking each individual drone, our Vicon system can also track small reflective markers on the user's hands, allowing for detection of touch events and move events by the BitDrone's operating system. Our system supports interaction primitives such as touching or dragging of individual drones across the Vicon space. We demonstrate a number of interaction techniques informed by traditional 3D user interfaces. Our country example begins with a top node representing the root folder. When touched, this expands into a submenu of PixelDrones, flying underneath it in a circular arrangement. Submenus can be browsed by unimanual horizontal throws of a single drone. When a file is opened, its 3D boundaries are indicated by PixelDrones, which act as handles to the compound object inside the 3D canvas. Drones can be dragged by holding them and physically move them to a different location within the Vicon space. Upon detecting a drag, drones will hover at their new position. When drones are dragged within the boundaries of an existing object, they automatically become part of this object. Touch operates similarly to a click in a graphical user interface. If a drone represents a folder in a menu, touching it reveals its content. A touch on a drone in a compound object selects the drone, whereas a touch on two different drones selects the entire object. DisplayDrones also sense capacitive touch within their display. And finally, compound objects can be resized by holding two drones within the object and performing a bimanual pinch gesture. Rotation is achievable by holding two drones and moving them in a joint arc. We also developed a number of application scenarios that demonstrate the versatility of our system. Since currently we can only deploy a limited number of drones at a time, most applications were designed with sparse 3D models in mind. So BitDrones can be used as a toolbox for architectural design. In this example, the user is building an architectural model using cubed ShapeDrones. The architectural design application is synchronized with a digital representation in Unity 3D, which allows users to run models and augment them with texture maps and shaders. BitDrones also allow for exploration of bonds between pairings of atoms. BitDrones can represent molecular structures in midair, allowing users to physically interact with them. To simulate chemical reactions, a user can manipulate individual atoms by dragging drones in or out of a molecular bond. We can also use our system to represent points in interactive data visualization. For instance, the position of a drone can be determined by a mathematical expression. Manipulating one of the drones can manipulate parameters of this expression, whereas other drones will adjust their position accordingly to preserve the spatial relationships as defined by the original expression. And finally, we developed a remote telepresence application in which users embody themselves via a remote display drone that shows a Skype video conference. This gives users the ability to fly around a model and interact with remote participants at eye level without requiring a robotic structure. So while our prototype is a first step towards interactive self-levitating user interfaces, there are a significant number of limitations we hope to address in future work. Our current implementation is limited to a small number of simultaneously flying BitDrones, which doesn't allow us to represent high-resolution 3D objects. If we consider a model of 1,000 voxel resolution, we would need 1 billion BitDrones, and while that may not be a goal that's achievable in the near future, we believe that efforts in miniaturization, as well as more robust control loops, should allow us to scale our system to hundreds, if not thousands, of self-levitating atoms in order to achieve the representations described in the intermediary steps in this picture. One limiting factor is downdraft, which restricts the ability of drones to fly directly on top of one another. Currently, BitDrones are only sufficiently stable to hover within 10 centimeters from one another, due to turbulence generated by drones flying in close proximity. The lack of pixel density and resolution pose challenges to support tasks that require detailed information and only allow for the display of relatively sparse 3D models. And the system as presented lacks robustness for a large number of repeated trials, which are technical challenges we need to address in order to conduct a meaningful and thorough evaluation of our system. But there are also a number of immediate goals that we hope to achieve in the next iteration of BitDrones. We are currently miniaturizing the design of BitDrones in order to scale up the number of simultaneously flying drones. We will add magnetic bonds, allowing BitDrones to connect to one another in order to mitigate the sparseness issue. We will outfit BitDrones with capacitive touch sensors for all touch and drag operations without the need for user augmentation. We will explore alternative geometries towards space-filling tessellations, and we expect to optimize position control algorithms to achieve sub-centimeter accuracy along each axis. We were able to achieve some of these by now. So as you can see in this video, we show a truncated rhombic octahedral BitDrone landing between two stationary drones in order to create an arc structure. So this somehow addresses the sparseness issue, as well as the flying on top of each other issue, because we are able to connect them in non-adjacent phases. So thank you for attending this talk and your attention, and I'll now take questions.
So again, if you have any question, please come to the center, give your name and your institution, and that's it.
Anu Chamji, University of Illinois, Chicago. Have you experimented with adding sound to the cubes?
Sorry, can you repeat that?
Have you experimented with adding sound like speakers to the cubes?
We have not. You care to elaborate?
I mean, these would be multimodal cubes if you had sound. Like they could give audio cues. I guess it would expand the applications.
I'll address that after. So no, and we're fairly limited in the number of augmentations that we can apply to the drones themselves. This is mainly because with miniaturization comes a compromise between weight to thrust ratio. So as we explore new geometries and as we try and miniaturize these drones, quadcopters may no longer be the most efficient way to do so, because we need a propeller clearance area around each structure, and the more weight we add, the larger this structure needs to be. So we did not explore audio, but that would be one of the drawbacks of having to add extraneous hardware.
Just to add to that, we did do some audio with the telepresence system, and so because the DisplayDrones are full-on Android phones. So we can even do this. We're doing this over Wi-Fi. It's just a regular Skype call. But one interesting application of BitDrones is for sound performances.
Yeah.
And doing visual performance, and we're definitely eager to explore that.
Okay, great.
But haven't yet.
Thanks.
Phil Wadler, University of Edinburgh. Where's the demo?
So we actually did travel with a couple of drones that unfortunately did not make the trip. So they are upstairs in the hotel room, broken to pieces. But we did do a demo at WIST, and we would be happy to show you them at our lab anytime you want to visit.
I'll come.
It's quite the setup.
Did you see the video session this morning and the winning video on using VR to make one cube appear as many cubes?
I have not.
I suggest looking at it because you might be able to use the same technique to make your one drone appear as many drones.
Absolutely. Well, thank you for the suggestion.
Jörg Müller, University of Aarhus. Very nice work. I wonder, could you tell a little bit of what you believe, what the limits to miniaturization are?
So right now we're running into the thrust-to-weight ratio. This may or may not be caused by the fact that we have yet to abandon the quadcopter configuration, mostly because at that scale is still one of the most efficient configurations that we have to for the payload that we need on each copter. That is only limited for right now to the wireless radio, flight controller board, and the motors themselves. There may be better geometries, such as counter-rotating propellers, a little bit like some helicopters work. This isn't something that we have actively explored to date, but it might be something that we might need to address for future iterations of BitDrones. There's also been work being done towards inspiring design by nature, so by mimicry, how birds fly with flapping wings and whatnot. This isn't something that we have addressed to date.
Yeah, but the plan is to, like, if you want 1,000 by 1,000 by 1,000 pixel model, you need 1 billion of them. Okay, and so they need to be also very small, and so you really need to start looking at insects and how they fly in these very viscous situations when you get to very, very small entities. And it's a largely unsolved problem. There's been some work in that direction. We do hope we can get there.
Great, thanks.